welcome to the last one of the semester. So we're going to go over liquid rocket engine sizing today. So pretty much the topics we'll cover, go through a quick introduction, kind of just introduce how rockets work, how thrust is generated, and how you kind of go through the equation of getting it, and then the various propellant combinations you could use, then go into kind of just sizing the engine. So nozzle sizing, chamber sizing, and then we could just step through all the things we talked about while using the Jessie and James example. So you can kind of get the idea how this chamber was sized in terms of the length, the diameter and everything. So, and then just a couple of things to note. This is just going to be focused on application and design decisions, and I'm not really going to go through the theory, kind of bore you guys, even though if I had time I would, just because it's sick when you know the theory and you can just derive shit, but I won't do that. So I'll just kind of go into, this is the equation you use. I can explain how, what it's made out of and what is important to understand from it. And I'm just going to assume everyone knows basic thermodynamics, fluid dynamics, and what a converging diverging nozzle is. Does everyone understand? No? All right. Well, then when I get there, I could just kind of touch up on it. So this is the ideal rocket equation. This is more used for the actual vehicle itself. So Alex, is this something that, is everyone kind of familiar with this? Yes. No? So this is kind of where the concept of staging comes from, right? So you have your delta V, which is essentially, if you're a contractor, right? So say you want to put a satellite and you use the Falcon 9, you're going to need a certain delta V to get you into an orbit. And then from there, you could use this equation. So this is your U equivalent, so your equivalent exhaust velocity. And I'll go more into that in a little bit. But essentially, this is the speed coming out of the flow coming out of the nozzle at optimum conditions times the ln of your final mass of the vehicle over the initial. So this kind of here shows that this determines why rocket engines are 90-something% propellant, because you need a big ratio here in order to have more efficient delta V, and that's also why you need staging, because you can't do it with one stage currently. So I won't go much into that, but that's just kind of where that stems from. So you kind of start off there, and then you can go into sizing the actual engine. So I guess we'll start off. Does anyone know the difference between a rocket engine and a jet engine? Yeah. No? Someone want to give the answer?
For jet engines, basically you use the atmosphere as an oxidizer and you provide the fuel. And for rocket engine, you provide both.
Yeah, so it's exactly spot on. So for rocket propulsion, rockets bring their own propellant, both the fuel and the oxidizer. So you can see here, just a general setup. You have your two tanks, and then those two provide the propellants into the engine. Main reason being there's no oxygen in space, so you need to bring it with you, right? So versus air-breathing propulsion is, David mentions, it uses the environment to take the oxygen, right? So you have a jet engine, takes the air, comes in, goes through a compressor, and then they inject fuel into it. And so this is the same way car engines work. Pretty much all engines use the environment, right? Why not? It's free mass. So even though there is companies like the one in England that's using both air breathing and rocket combined, which would be pretty cool. But so that's the main difference, just so everyone's on the same page. This is a general basic, the architecture of a launch vehicle, right? So just going across, you have your tanks, and so this would be for a turbo pump, which is typically used for launch vehicles, because the way right now we have pressure-fed engines, and in order to have essentially a pressure-fed engine means you need high pressure gas to push the propellant into the engine, right? And so that means the tanks need to withstand a high pressure, and so that means the thickness of the tanks need to be quite thick to hold that pressure, and now all of a sudden the mass explodes, right? So the way that all launch vehicles work is that they have these running at as low as pressure as they can, and then they'll use turbo pumps to pressurize it, and so then therefore none of this needs to be rated for high pressure. And so even though the pumps may weigh something, it's a lot more mass saving than having thick tanks. So that's pretty much a general setup. Then you have your combustion chamber, and then the nozzle in your engine. So this is probably the deepest I'm going into the whole entire launch vehicle, and then now we'll just focus on the engine itself. So thrust generation. I kind of like this analogy. I'll mention it if I ever, talking to someone that is new to this area, the way to think how thrust is generated in terms of energy. So if you think of this as your launch vehicle, right? Your propellants is your potential energy, right? So you have these propellants, a fuel and an oxidizer that have energy inside, right? And as well as you pressurize it. So whether it's pressurized in the tanks or you use pumps, then you gain more, potential energy. So there's a lot of potential energy there. And then you go into the combustion chamber, and you take that potential energy, you combust it, and you pretty much obtain a bunch of thermal energy. So you do that conversion, and then right after the nozzle is the kinetic. So you take all that high heat pressure, and you just kinetic energy. You just accelerate it as fast as you can out the nozzle, right? And so that's essentially what you do for a rocket engine, is those three, and that kind of mentions it there. So with that, you have a bunch of, this all kind of relates back to Newton's third law, right? So for every action, there's an equal opposite reaction. So you have a bunch of propellant flowing out the nozzle, and therefore the force going in that direction is going to generate thrust. Your rocket's going to move. So I won't go into it until all these equations, but this is essentially what you obtain. So this is the thrust equation for a rocket engine. As you can see here, you have the thrust, and it is equal to this stuff over here. So this is your mass flow rate and your exhaust velocity. So how fast you could flow your total mass flow rate, right, out your engine, and how fast it's moving out the engine, plus your exit area. So what the exit area is of your nozzle times the difference in pressure. So the difference in pressure, meaning the PE here, means the pressure right at the exit here versus the pressure around it in ambient. And so that kind of goes back in the beginning when I was saying this is your equivalent velocity. So if you think about it, right here, your PE minus PA, right? So your PA, if you think of a launch vehicle taking off into space, you're on the ground, it's at sea level, right? And so as you're launching, your pressure is slowly going to zero, right? And ultimately in space, there's no pressure. So at any given time when a rocket's moving, this is changing throughout, right? And so it's kind of complicated to figure out in real time what it's changing. And so a lot of the times you'll simplify equations, and this kind of gets to the equivalent exhaust velocity, which is when it's your optimum condition. So it's when PE equals PA. And so that essentially will give you the most thrust, is when you're able to expand this flow so that it equals what's outside. I think I might have a slide on that coming up, but yeah.
If it's optimal when P equals PA, but then on the right it's P minus PA, so when you want P to be greater than PA, it's like a positive term to get more.
What were you saying? Oh, so you're saying you want that to be higher? So the reason that is not true
makes UE lower, isn't it?
What? UE would be lower.
What
variables does your exhaust velocity depend on now? It would only be...
We'll go into that into later slides, but what was the reason again? It has to do with your P equals PA. You start having losses. So your nozzle will be overexpanded or underexpanded, and then if that's the case, your flow.
So I do think the thrust will be greater when you go higher, but the efficiency the efficiency of the whole thing will be lower, but the absolute thrust.
I think you're right, and I think that has to do with what does it do, the flow of the nozzle. It's kind of forgot in my head. I know this because I remember I thought that exact same thing. I think it's because this ends up being lower, if I'm correct. I don't know if anyone could comment on that. Yeah.
I think UE is also a function of the exit velocity. So when your PE is higher, I think you didn't expand the gas as much.
Yeah.
And then the UE just dropped.
Yeah.
I think that's true.
Highest speed is dependent on the exit pressure.
Yeah.
So as long as the higher
Depends on
pressure is
the
supposed to
There are two forces.
Yeah.
So one force is
Yeah.
caused by the chamber pushing outwards.
Yeah, it's because you're right, John. It's because UE goes lower.
Yeah.
We'll get, you can think
I
of it to
think-
the ISP equation,
Yeah,
which is
the ISP will determine it, but
Yeah.
Average of is more.
Okay, yeah, sorry.
yeah, no, that's a good question.
I mean, yeah, we need to check out the information.
Yeah.
Because yeah, I mean,
Okay.
So I think that's what it was, and
Yeah.
I think later on there's an equation.
Across your section.
Yeah.
Yeah, I think there's an equation later on that that I think will show that relationship. But I believe that if this ends up not being optimal, this will be lower, and so essentially it'll not be as high of a thrust as if it was equal to each other. But when it is equal to each other, this goes away, right? This becomes 0, so this whole term goes away. And that's why a lot of the times you'll see equations that say thrust equals m dot times UEQ. Yeah, and that's actually why, because U equivalent actually equals UE plus this. So that's why. All right, so specific impulse. This I'm just mentioning because you hear it a lot, and I feel like a lot of people are just like, what the hell is this? So specific impulse, it's in seconds, the units. Sometimes it's not in seconds. I think the Russians don't use it in seconds, but don't have that written here. But everyone else uses it in seconds. So it's this general equation. So U equivalent, which I just mentioned, is UE plus this stuff over here over your gravity, Earth's gravity. So that's just a number that that you use that. So if you're talking about the ISP on Mars, a rocket engine on Mars, you still use Earth's gravity. So that's like one thing. If you take like Grumman's class, they'll try to trick you to think, that's one thing they make sure you know. So this ends up being in seconds, and the other way, like the ways that you could describe it is these two ways. So total thrust over the weight of the propellant, or the thrust over the weight of propellant consumed in 1 second. And so it might not make a lot of sense, but the best way I like to think of it is essentially equivalent to when you think of gas mileage in a car, right? So when you're buying a car, you want more gas mileage. That's a plus, right? It's pretty much a negative. If there's no reason why you would want. If it was the same car but one had 20 and one had 10, you would obviously choose the 20. And so for chemical propulsion, that's 100% the case. Higher ISP, better. Electric propulsion is not the case because you have to take into account the mass, but we're not talking about that, so you can kind of ignore it. So I like to make that analogy, and so it's essentially how efficient is your conversion of propellant energy into spacecraft impulse, right? So how can you take that energy in the propellant and turn it into a quick impulse? How efficient is that? And so that right there tells you that ISP is a function of the chemistry. It's a function of your propellants. So it has nothing else to do, it has nothing to do with the geometry or anything like that. It's solely your chemistry is what dictates your ISP. So this here is like a quick table of various ISPs you can get for different types of chemistry. So you see up here is solid. So solid propellant, you get an ISP around 220 to 300. Monopropellant, so does everyone know the difference between solids, monopropellant, and bipropellants? Yeah? No? All right. So solid is your solid rocket motor, right? Like RPL does. You put a bunch of grain in there, you light it like a bomb, and it flies right out, right? So that's what solids are. Monopropellant means one propellant, right? So essentially, that'll be like hydrogen peroxide, hydrazine. And the way those engines work is you take that one propellant, you put it through a chamber. But the difference is here is that chamber is made of a bunch of transition metals that react to that. So right when it contacts that, hydrogen peroxide, H2O2, it all of a sudden turns into H2O, O2, right? It just completely, the contact of the surface is what does the chemical reaction. There's no two things you're lighting. So, which is good, and that's why you'll see like hydrazine is used like on like where things like that need to work. You'll see those sort of things. But the downside is your chamber erodes over time, and you need to take that into consideration. So, but as you can see here, for monopropellant, you don't get as much energy generated from it. So you're around 150 to 230. Liquid hydrocarbons. So this is your kerosene LOX, your methane LOX. So anything with a C and an H in it for a fuel, it's your hydrocarbon. So that'll give you 250 to 350. And so this is what we use, right? So for our kerosene or if we use Jet A fuel or RP1, that's this form here. And so you'll get a little bit higher. The best, the optimum, other than you could use other, so this is liquid hydrogen in LOX is the best, 450 ISP. And you can see down here, these are the different engines that you guys are probably familiar with, and they have different chemistries, right? So you can see on the left here, this is the Saturn F1 engine, right? So these are 5 of these are on the first stage for the moon rocket. This is made up of RP1 and LOX. So we're in this zone here. So the ISP here is 300 seconds. And then the SpaceX, the new Raptor engine that they're making for the Mars vehicle is 360. So I guess it's a little bit higher than this. I think it's because they use, I believe it's because they use densified.
Higher chamber pressure.
Yeah, it's a higher chamber pressure too. So yeah, this is actually going to be the highest chamber pressure engine, like 300 bar, I think is what Elon is pushing for, which is going to be the highest chamber pressure by quite a big amount. So that's 360, and then you have the Space Shuttle main engine, 450. And you can tell here these different chemistries give you different exhausts, right? And so you see the kerosene is a ugly yellowish color. You know, this is a pretty cool looking purplish, and then it's clear for the, yeah.
So I feel like I've seen a couple different companies' engines have the same fuel and oxidizer with a different ISP. For some biprop engines, is the ISP also determined by the ox ratio if you're working with the same propellants?
Yeah.
Okay.
Yeah, so it has to do with that and chamber pressure. It's essentially how efficient you can make the combustion happen, right? So I'll go into that briefly coming up, but yeah, that'd be a short answer, yeah. Any other questions? No? So does anyone know, so what's coming up next is, you know, why doesn't everyone use liquid hydrogen in LOX, right? Like if it has the best performance, why not? So I'll be discussing that coming up. So your propellant choices. So this is a design choice that, you know, everyone needs to make in the beginning. So what propellants are we going to use? So these are different things. I'm not going to we're not covering this in full right now, but these are just different things to think about. Storability, right? So is it something that is cryogenic, right? So cryogenic meaning it's really, really, really cold. You have to keep it really, really cold. So if you think about it, it works for a rocket engine, right? Because you put it on the launch pad and you have the day set a month in advance, and you launch your vehicle at that 1 second. But if you're talking about a military ICBM that you have, you know, Russia shooting a missile towards us and we launch one back, like if it's cryo, where is it going to be stored? You know, that's why they use non-cryogenic, and so those could be underground at any second. Press a button and they fly out. So these are all different things. So toxic. So is it hard to be around? Do you need to wear a lot of PPE when you're around it? Is there a lot of regulations, you know? And so there's actually, I forgot what it was, it's been a while since I take like advanced propulsion, but there's a better chemistry than liquid oxygen in LOX. I think it's like fluorine or something like that. You get a higher one, but it's like nasty stuff, so people don't use it. Because if you think about it, there's a lot of things when you have to move it around and play with it, it's going to be a ton of money in terms of making sure everything's safe, so then it might not be worth it. Stability, right? So those monopropellants, if they touch any transition metal, it completely goes wild, right? So some of those things you need to make sure are very contained and monitored all the time. So all these things are played to effect. And then your heat transfer properties, your density, the freezing point, the energy within them. So these are all things. But so now we kind of will move towards the thermodynamics. So this kind of goes into the chamber in terms of taking that potential energy, like we mentioned in the beginning, and turning it into thermal energy. We're not going to cover this into detail right now, just because it could be a whole lecture itself. But essentially, what these thermodynamics or thermochemistry tells us is for a certain chamber temperature and the type of propellants you use, the type of propellants you use will have their own specific heat and your gamma, your specific heat ratio, and a bunch of things. Those sort of things end up telling you when you combust it, what sort of temperature are you going to get and what sort of mixture of the two things you're going to have, right? And all of those things will play a role into the whole nozzle, turning that now hot thermal energy into kinetic energy all relates. It's all nozzle flow that has to do with gases, right? So essentially you play around with these sort of things. There's a nice, like if you take rocket propulsion, you'll do this by hand, at least the first iteration. I don't know if the advanced, if you do, like, do you do more advanced ones? You have to do like iterations? No?
Don't think so.
So like when you do these,
Like decompositions. But
yeah.
no.
So essentially it could get pretty complicated. It took a while. You have to write iterations and things like that. What we use is NASA CEA. Someone wrote a software that does this in 1 second. So instead of using hand calcs, which take forever, you just literally go on this website, plug in values, and then it tells you what your chamber properties will be. And so that's the website right there if you need to use it in the future. And this is kind of what the output looks like. So if you look here, you have your inputs. So you have your fuel and your oxidizer. And then from there, your range of OF ratios. So like you were mentioning, different mixtures that's how you end up with different ISPs is this ratio. So you can play around how much fuel to how much ox. And then your range of pressures. So you can play around with a bunch of ranges, and then it outputs this sort of stuff. So this is the things you care about at the end of the day. What your chamber, you tell it a pressure, but you end up receiving the temperature in the chamber, the density of your combusted gases now, right? So it's not just you have some oxidizer, some fuel, right? So what ratio it is, what density is that, what specific heat, what gamma, what ratio of those is it? And so this is pretty much all I'm going to be covering on the thermodynamics. So essentially, and this is what our GUI does too, you tell it all this sort of stuff, and then it tells you what the chamber pressure is, your gamma, and density. I don't even think you really need density to solve much of anything, but that's essentially all you use NASA CEA for. And then from there, let's see. Okay, yeah, so this actually goes back into a few things. So when I was talking about over here, why doesn't everyone just use liquid hydrogen? Does anyone have an idea why? Why not just for every engine use that? Because they're both cryo, right? So for instance, SpaceX, other than the whole thing that methane's on Mars, and other than it being cryo, is there another reason why you think liquid hydrogen isn't used all the time? It's light, right? So it's really light, and so that means if you want a ton of it, you need a huge tank, right? So it has like the lowest molecular weight. So, and then all of a sudden your tanks are big, and then all of a sudden you have a ton of mass, and then if you go back to the original rocket equation where it's the final mass over the initial mass, then it kind of like ends up being all right. It's maybe not the best. And then there's also a whole other thing that if you take the launch vehicle design class, it'll go into, if you ever notice, every single launch vehicle typically uses kerosene blocks is for the first stage, and then the second stage might be you might use liquid hydrogen, and it's because of the density. It's like per unit density, because essentially you need to try to bleed as much out in the beginning, and so you want denser things for your first stage to overcome that initial gravity you have. So I won't go too much into that, but this is the equation for your exhaust velocity. And so this has to do with nozzle flow, and I'll go more into nozzle flow later, but I'm just showing this here to kind of show relationships. So this is the sort of thinking that as an engineer or designer you need to be doing in your head. So this equation here tells you your exhaust velocity, right? And so we just saw from the rocket equation, we want this number to be as high as possible, right? We want it coming out as fast as possible from our nozzle. And it equals this sort of stuff. So you have your R. Your R is a universal gas constant here, so that's just the same number. Your gamma is what NASA CEA told you, and that has to do with your OF ratio, right? So if you have more of something that's lighter, it's going to end like that has to do with your combustion. And then this is pretty much the main thing that dictates a lot of things. It's the T naught over M bar. So this tells you right here that for a higher temperature, you're going to get a higher exhaust velocity. So ideally, you want a higher temperature. But then it's over your M bar. So it's saying that if this is larger, then now it's going to be lower. So you want this to be as light as possible, and this to be as high as possible.
Sorry, what's M bar?
M bar is your molecular weight of the material of the combustion itself. So your fuel and your propellants. So if going back to the costs and benefits is hydrogen, the lowest molecular weight, has the highest ISP. That's also because it has the lowest number here, right? So that right there shows you what that is. And then the higher the temperature, the better, because you have more thermal energy that you can convert into kinetic, right? So
That's your chamber temperature?
yeah. So knot, wherever you see a knot, that means it's your stagnation temperature. Stagnation temperature means it's a made up thing. Stagnation variables don't exist. What it's saying is, if you have a fluid, it's comprised of potential and kinetic energy, right? Anything has kinetic and potential energy. It's saying, so take this fluid and we're going to completely bring it to rest, right? So bring it so that it's not moving, and therefore everything is converted into potential energy, and that's what that value is. And so for the combustion chamber, you could think of it as a reservoir, right? So something that the speed that the combustion chamber, that the products are making, like the moving in the combustion chamber, is peanuts compared to what it's coming out of the nozzle. So that's why essentially you could assume that the velocity in the chamber is 0. It's like very, very close to 0. And that also has, the Mach number is pretty much 0. And that also has to do with,
Are you talking about macro velocity or thermal velocity?
I'm talking,
Okay.
yeah. So your Mach number is essentially 0. So
Okay.
that probably would have been a better way to explain it. So that's saying you're going to bring your fluid to Mach number equal to 0. And if you think about it, your Mach number is your velocity over the speed of sound. And your speed of sound is the square root of gamma RT. So if that T is really, 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 really high, then that means that A is big. And if A is a lot bigger than U, which is the velocity, it's 0, right? And so you have really high chamber temperatures in there. So essentially your Mach number is going to be 0, or really close to it. So, yeah. Don't remember where that was getting to, but essentially, yeah. This, and then so you look at here, that's where this mentions here, you want the highest of this ratio as possible, and that's why hydrogen's really good. And so that will give you a higher exhaust velocity and higher ISP, which I just mentioned with the hydrogen. Then this is another thing here. So decreasing gamma, which is a result of your NASA CEA, your OF ratio and what your propellants are. By decreasing that, we'll increase that, and increasing your pressure in the chamber, because it's not there, increases your UE. And so if you just, like, for instance, this one, if you look there, it's in the denominator. And so if you have a larger denominator and you raise it to something, it's going to be a smaller number. And so when you take 1 from it, it'll be a larger number, and then therefore it's larger.
How close to 1 can we get gamma?
That's a good question. I would not know that off the top of my head. Someone else maybe?
Depends on what kind of molecules you're looking at. So gamma is basically kind of like the internal kinetic energy contained by the molecules. Like say the molecules has multiple atoms inside, the gamma will be greater. If it just has 1 atom or 2 atoms inside, the gamma will be smaller. But the rough number is usually from like 1.2 to 1.8 something. But never I never seen something above 2. It's really, yeah.
Yeah.
Do these equations only apply for liquids or also solids?
It applies to nozzle flow, so it would be the same for solids. So the only real difference between a liquid and a rocket engine is the combustion process, like what it's combusting. But at the end of it, the day, like if you go back to when I was saying your thermal, like your potential and your thermal and kinetic energy, at the end of the day, you're taking hot stuff and you're accelerating out of a nozzle, whether it's a liquid or a solid, it doesn't matter at that point, it's a gas, right?
Yeah.
So this is sort of the stuff that changes, and then that stuff is typically the same. Giant's got a lineman.
Rojo went 38.
Did he? Alright, yeah, sorry, my phone's blowing up. My texts are blowing up. Alright,
Slide. You missed one.
I missed one. Alright, so the CEA results, what's it saying here? Okay, yeah, so you want the highest temperature, right? We just saw it in the last equation. That happens when you're stoichiometric, meaning that it's the perfect combination, right? So if you ever took that chemistry class and you have your products and your reactants, the perfect ratio when you do your equation, like that's what you want of each, the amount of fuel and the amount of oxidizer, and so that will give you the highest temperature. But essentially we just saw like, yeah, that's great, but at the end of the day, we want this ratio to be the highest, right? And so if you think about it, then depending on what it is, the composition, you might have more oxygen, more fuel, and if something's heavier than the other, that's going to change. And so essentially this ratio at the end of the day is what really matters. And so you'll see here, this is where, what is this for? This is for kerosene. Do you remember
RP1 oxygen.
RP1 and ISP. Oh, okay, yeah, right here. So this is the most efficient, and this is like the highest temperature. So we'll be riding on the fuel-rich side, and then it kind of is a trade-off from there. So we'll talk about that. Okay, yeah. So in terms of what pressure to operate at, right? So if you have a higher pressure, you have more potential energy, right? And so you'll be able to ultimately convert more energy into kinetic energy, which is going to give you more thrust. So the higher, it will give you a higher ISP because it'll be more efficient for when you combust things as well. But by having a higher pressure, now you have more stress, right? So now your walls might need to be thicker, a bunch of things you need to worry about because it's more pressure. And it's going to end up more weight, which is now going to affect the rocket equation getting off the ground. And so you need more feed system weight. So that's one side. And then you'll have a higher temperature. And then the higher temperature means you need more cooling. And so it's kind of like a design, finding what works for your application. And then the OF ratio. So like where do you want to end up being at? So ideally you'd want to operate like right in this range. But at the end of the day, you might not be able to get there. And so you end up making these trade-offs of where you want to be at. And different things could be like, for instance, Hydra. The reason why we're running at that operating condition is because it's the most we can pull out of Hydra. It's the most we could pull out of Hydra. And so that's kind of where it ended up being. But then it's also like, your mass flow rate plays a role because your original equation is I'm not going to go all the way back, but it's your m dot u equivalent. So you want as much propellant to go in as possible. So that's also another trade-off. Your OF ratio. So usually you'll be on this line here, right? And so you'll hear terms a lot of the time like, oh, you're going to be more fuel-rich or ox-rich. It's essentially, you're always, like, at least for this, you're always going to be fuel rich, but it depends. Like, the more oxygen you have, the hotter it gets. So that's typically like the rule of thumb. Like, if you have more oxygen compared to fuel, it's going to be hotter. Because oxygen, when it combusts, it's hotter than more fuel. That's why for film cooling, we blast it with fuel, right? Because then when that combusts, it's not as hot as when it's not. So that's like the concept of film cooling.
Wait, I'm sorry, could you say that again?
Yeah, so the OF ratio, if you have more oxygen, then it's going to be hotter. Because when they combust with each other, it's going to result in a hotter temperature. And so that's why you'll see film cooling is literally you'll put fuel, you'll blast something with fuel that has like a little barrier, because then when that area combusts, there's more fuel than oxygen, and so it's not as hot as when it's not. And that's why you'll see most like pre-burners, which is like combustion chambers before the combustion chambers, are usually always fuel rich because it's not as hot, and so it's easier to thermally control it. But it's always a trade-off. So lower temperature, lowest ISP, higher temperature, higher ISP. So it's like, where do you want to be? And that's also why you see different engines with different ISPs. But the range is still, you can't get much higher with the chemistry than what those graphs showed. All right, so now we'll move to the nozzle. So this is pretty much where the most of the sizing happens. So now we're trying to convert it to kinetic energy. And so this is the bread and butter. Like if you take compressible flow or fluid dynamics, you'll touch this stuff. And so you always start off like in those classes with a bunch of assumptions, because it only works if all those assumptions are met. But it turns out that rocket engines actually behave like this. So this is quasi 1D steady isotropic flow. Those are all the assumptions made for a nozzle. What does all that mean? So you have quasi here. It means that it involves a slow varying cross section. So that means if you looked at the nozzle, the area it's increasing, but very slow relative to like what it relative to like the distance. It's like a very slowly moving, and so that's where the quasi comes from. The 1D means that the flow properties are only changing in one dimension. All right, so if you end up doing all the derivations, which like I said I'm not doing, you'll notice that the only thing that's changing is along the axial length of the nozzle. So at any given location, your pressure, your velocity, etc., is going to be uniform all throughout that cross section. It only varies as you go down, and so that's another. That's a big assumption there. And then the steady means it's not changing in time, so it's a steady. So you couldn't use these on startup, but not changing in time. And then isentropic, which means it's adiabatic. That means you're not adding any heat to it. It's just what it is. No heat is coming from the environment. And reversible, so meaning no entropy is lost. So essentially, this ends up being a very, very good approximation. And so that's where this kind of everyone sizes their engines to this because it's very close. I think it's like 90-something% correct. And then you'll have these other equations, which is like was it CT and C star, I believe?
Yeah.
CF? Yeah, and so you'll have these other equations that compare it to reality, and essentially the closer you can get that number to the other one, the more efficient it is. So going into these, this is the one big equation here to ultimately that talks about nozzle flow. So this is your area Mach relation. It's a very everyone knows this for rockets. Like when I have interviews, like they'll ask me questions on this equation to see if I understand the concept, because the concept's important. So what this means is the Mach number is only a function of area. So kind of what I mentioned here with the 1D flow, that it's uniform at any given cross section, right? So the velocity is only moving in this direction, the temperature is only changing in that direction, etc. So your Mach number, you can see in this equation, the only thing that affects the area here is Mach numbers, and your gamma, which changes technically. Your NASA CEA will give you something in the combustion chamber, and technically it changes throughout, but it's very minor that you can kind of just like neglect it. But it does change because it's dependent on other thermal properties. But it's only a function of Mach number. And so what that means is if you want a certain velocity, at the end of the day, you want a certain exhaust velocity, right? Your UE, it's a function of your area. And so the larger the area, the more thrust is, the more, what's it called? Velocity is flowing out. So, I guess what's the best way to put it? I guess it'll make more sense when you go through the equations, like coming up, but essentially just know that. And this cannot be solved by hand, it has to be done numerically. Like you cannot solve for, if you know a certain area ratio. So another thing that I should probably mention is the star here means throat. So typically in industry, if you see a knot, that means the chamber conditions of a subscript. If you see a subscript of a T, that means a throat. Or if you see a superscript of a star, that means throat too. Actually, it says it right here. So this means the area between the throat and whatever area you care about, right? So you could use this equation wherever. So if you're interested in the area at the exit, right? If you want to know the Mach number at the exit, you know the area at the exit, right? You can just measure it. And now you know this, and so now that's an E, right? And so that's what this kind of mentions. You just plug an E wherever, right? This is 2/3 down, then that's the Mach number 2/3 down, etc. So this is pretty much the trend of what happens with all your fluid properties as you go throughout the nozzle. So let's see, what's the best way to look at this? T star. Actually, I don't know if this graph does that. But all right, so what this graph shows is your isentropic Mach number flow relations. And so this is back to that thing I was talking at the beginning. You have a flow and you accelerate it to, you make it to, you can relate your Mach number to a certain temperature using your stagnation properties here, your like made up properties. So you use this equation, you find your exit area, right? If you care about your exit, you find your Mach number at the exit, and now from there, you know your MEU, right? So if you put ME here, you know the temperature at the exit, you know the pressure at the exit, the density of the exit, you know everything now. So that's pretty much like the thought process if you want to find out anything. And then these are just showing how things change as you go down. So essentially, as you go through the nozzle, your temperature is going to decrease, your pressure is going to decrease, and your velocity is going to increase. Those are like the main trends that you'll see. And so essentially, you always want your exit to be equal to your atmosphere. So, and that's kind of why you'll see the difference between a sea level engine and a vacuum engine is the vacuum engines are huge, the nozzles, right? And that's because you want PE to equal PA. And so in space, ambient is 0, there's none. So you need a longer nozzle to take that kinetic and the thermal energy and convert it to kinetic energy where PE equals 0, essentially. So you need a longer, right? And so this is slowly varying, so you need more room to go. And so you keep going until this equals, that equals what's outside. So, yeah. Then essentially, out of all that, this is what you need to know. You literally just use this equation to figure out what the throat area needs to be, which is a function here, as you can see. This is the total flow rate, mass flow rate, over your chamber pressure. So this kind of dictates what this needs to be, these two parameters here. So you could have a nozzle that's made for 1,000 PSI, but it also is for a certain flow rate. So that equation is what you would use, and then this is assuming optimum expansion at sea level. This is what your exit would be. So where PE equals PA, this is your exhaust. This is the Mach number you need at the exit for that. So does anyone have questions? I don't know if I've lost people, but yeah.
Just generally, I'm trying to understand the idea. You said velocity increases as you go downward,
Yeah.
down the nozzle. Like, just conceptually, that probably would be really. Can you explain it?
It's now in supersonic. Because when you add a throw, you're at some, and I think once you pass that, it's supersonic. So in subsonic.
Okay, yeah, this was I forgot. So this is the whole like converging, diverging, which I assumed everyone knew. So it's pretty much what David's mentioning is the way your rocket engines work is you assume this velocity, the Mach number here is pretty much 0, right? And so the way converging, diverging nozzles work is they use flow. And so the way flow works is if you accelerate it to Mach equals 1, and then all of a sudden you have an area that's increasing, the flow actually goes faster. And that's because what's happening is, so everyone knows, like for instance, when a plane goes across the speed of sound, it makes like a sonic boom, right? So when that happens, it generates a shock wave. And so when that flow passes through the shock wave, it's all of a sudden a huge pressure difference, and that's what generates a shock wave. And so across the shock wave, your flow all of a sudden is going to go subsonic. And it's kind of the opposite when you're at Mach equals 1 and you open the area up. What happens is something called an expansion fan. So it does the opposite. So whatever you would think would happen is actually like the flow. I guess the best way to think of it is if you have like a hose, for instance, and you have water coming out of it, and you put your finger there, it's going to come out faster, right? And that is because the area has decreased, and so now all of a sudden your velocity is going to increase. But it's opposite when you're above, when you're supersonic, is that if you actually decrease the area, the velocity is going to go down. And it has to do with a bunch of like theory and using your conservation equations, which I won't go into it, but if you're interested, like, I could always do another one later or show you where you would read up on that, but it's backwards, and that's why it doesn't make sense.
So quickly though, so one fundamental thing about the throat though is you really want to reach m equals 1 at the throat.
Yeah, you need to. Yeah, so that's the big thing there, is you need Mach equals to 1 for this to work, right? Because if what happens is, if you don't have Mach equals 1 here, and you're subsonic, then now the traditional thing where you have a larger area, it's going to slow down, and that's what's going to happen, it'll slow down. So you need Mach equals 1 there because that's like your transition, And so then if you increase the area, you have the expansion fans, and now it actually increases the flow. So yeah, that was a good point, I forgot that. So that's why it's always critical to get the throat correct. The end here doesn't really matter too much, because if it's, so you want P equals PA, but if you were to, but we also just mentioned when your rocket's launching, your pressure outside is changing 24/7, like literally every second it's a different pressure. So it's impossible to have P equals PA. So you kind of find where something happens, and that's where you have overexpanded and underexpanded. And then you'll notice, like if you watch like a SpaceX video, the plume just becoming huge, versus not. And so that has to do with that. It's not too critical, but you just won't have the best performance, right? You might have losses due to like the coming off the wall because it doesn't have enough pressure, and you'll have certain shocks generate, or if you have like an overexpanded nozzle, that's where you see the Mach diamonds, right? The famous Mach diamonds. So yeah.
I imagine this is definitely already been looked into, but like, why don't you just have, why is there a thing where like you just have like a sensor loop where like it detects the pressure inside of a variable nozzle, like you can change the...
Yeah, so that's looked into, and that's kind of what the Aerospike does. It like makes that always perfect, the Aerospike engine, if you ever looked it up. It's just really hard, because then now that means you always need to be changing your exit. You're talking about to P equals PA?
Yeah.
Yeah, your exit always needs to be changing. So how are you going to put more material and take material off? Things need to be moving.
Yeah.
It ends up like not being, people don't do it because it's not easy, I assume.
But
that's why it's not done.
If someone did it, it would be...
Yeah, and that's what an Aerospike is. I mean, I can show at the end like a video of Aerospike, but the concept is it's like a bell-shaped nozzle, but it's backwards. It's like inverted. And so your exit, it ends up like creating like a layer where P always equals PA, and so you get the most efficiency. But at the end of the day, like the amount of thrust you lose isn't like the end of the world. Like we're talking like not too significant. You could get it elsewhere. So I think it's probably more the amount of money and resources it took to develop that is not worth the result you could get, I guess. That's why it hasn't done, or they're lazy. So. All right, so that's kind of nozzle flow. You just figure this out, and then once you know your Mach number, like I just mentioned, you can figure out every other property in the world you want to know at any given location in a nozzle. And you always want P equals PA. So now we have the nozzle, you can size the nozzle, and now what about the chamber, right? Like, what does the diameter need to be? What does the length need to be? All that, right? So that's the other side now. So how do you size that? So now we know the throat area and the exit area. And now what should the combustion chamber be? So this is like a traditional way it's been done. It's this L star that you'll hear people like throwing around. And so L star is like a certain characteristic length for a given chemistry. They'll give you a certain L star. And there's like a little range. So essentially, you pick one of those, and that's just based off of other engines in the past. Like this is end up what the traditional L star is, right? They come up with a characteristic length so they can compare all the previous engines that came before it. And so that's where that is. And we just determined the throat area, right? Because we need Mach equal to 1. So now all of a sudden we know the throat area. And so now we can figure out the volume of the chamber. So this is a table that I'm just talking about. So this is like in one of those textbooks. So different chemistries here have different L stars. So we're operating for kerosene, yeah, we're like in this range, which is L stars in centimeters, which ends up being around like 50 inches is this. So I think we did the higher end of this, and I think the thought process was that we don't know how efficient our injector is, or the combustion is going to be like optimal, so like let's just have more volume to like be on the safe side, right? Because essentially what this is telling you is you want to have when your things are combusting, you want to have you want everything to combust perfectly, right? So you want to allow enough volume for that to happen. So these are kind of the design trade-offs. If you have a very long and narrow chamber versus a short and fat chamber, so that just means your volume, right? You'll have your area times your length. So if you have a very long but short area, this is what happens. This is sort of the result. So you'll have more pressure loss due to friction, more heat transfer in the walls. So that means you're going to have more surface to cool, right? So you need more cooling. There's a longer surface Cool. And then short fat means higher hoop stress, so you need to have thicker walls. So these are kind of like the trade-offs between what do we want. This here is just a cheat sheet. If anyone ends up wanting on their free time to just like design a rocket engine from scratch, like these are the equations you would need. We just went through them all. Your thrust. This is your exhaust velocity, depending on the chemistries here, and your pressure. And then your area Mach relation, which now tells you your ME, right? And then now your ME tells you all this, and now you can check your PE and check if it equals PA, and if not, then you're not at the right Mach number, right? So you're not at the right area ratio, so it needs to be longer, shorter, etc. And then this is what we just went over. And then that is, that's your throat area and your Mach at the exit. So now we'll just step through essentially what we did for Jessie and James. And you can kind of see everything I just spoke of in the actual numbers punched out. Any questions before I do that? No? All right. So this is kind of what I explained in the beginning, right? So we determined our total MDOT based off of what Hydra could do. And then from that, we were like, all right, that just gave us an OF ratio. And then we compared that to that graph, and it ended up being kind of nice. Like that's kind of near the range. Does anyone, Mike, do you know what that was? The optimal?
Optimum was around 2, actually.
Around 2?
Yeah.
Yeah. So.
Well, 2. Yeah.
Yeah, and I guess I don't know if this is going way overkill, but like why didn't it then also is another trade-off between we can get this MDOT to equal the best T naught over M bar, like the optimum chemistry that can go. But then if you look at that, the ISP is literally this U equivalent, right? So when that equals 0, it's M dot UEQ. And so this is your chemistry, and this is how fast you can throw stuff out of there. And so then it kind of comes a trade-off as, do we want to be more near like the most optimum combustion, or do we want to just throw a ton of shit out? Which one's going to give us a higher thrust? And that's kind of what we did, right? And it ended up being the highest thrust at the end of the day, ended up being those combinations.
2 questions. First of all, for total MDOT, is that peak MDOT or average MDOT, or how do you,
so
what number do you pick?
MDOT, so going to fluids, that's the one thing that's conserved. So going back to like fluids, you have like your governing equations, your conservation of mass, momentum, and energy. And so conservation of mass is saying if you have a control volume and you have so much coming in this way, it's going to be so much coming in out that way. So that right there dictates your mass flow rate is going to be the same. So for a steady state condition,
steady state. Okay.
Yeah. So if things are changing upstream, or if the throat area is expanding, right? Because like we saw when we fired in December that the throat is changing, then all of a sudden that equation I showed you in the beginning, which was the P naught, M bar over P naught, those will like start compensating and changing. But in a steady state situation, yeah.
Right. Okay. And then can you go forward one, please?
Like back a slide?
No, the other way.
Other way. Yeah.
Oh, yeah, and as far as OF ratio, is that mass ratio or molecular ratio?
It's be the same. I think mass flow rate. I think mass flow rate is, but it might be the same.
Mass
for both.
ratio.
Yeah.
Okay.
So it's how much mass per second leaving your control volume.
Gotcha.
So yeah. So with these two numbers, you could determine how much mass and how much fuel you need to be pumping out in terms of mass flow rate, which is will be on the next slide. But so this is your design point, right? So this is things that we determined up front. What Hydra could do, what ended up that OF ratio, chamber pressure. We picked 100 psi, 1,000 psi because we wanted to have the highest operating rocket engine ever by university. So that's why it's 1,000. And 69 bar looks sick. So but just put into context, like the Raptor engine is gonna be 300 bar. So you can do that conversion to see what psi that is. It's pretty fucking high. And then your PE, we know. We're designing this engine for sea level. We know what the pressure is at sea level. And then our L star we saw from that graph, right? 50 inches. So we know this. This is our design point. Then from the thermochemistry from NASA CEA, for kerosene and gaseous oxygen, these are our conditions in the chamber. That's our temperature in there. That's the molecular weight now of that OF ratio. And that's what the specific heat ratio, gamma, ends up being. So, yeah. So now that we know all this, now we step through these equations that we just went over. So this stuff here is the front part, right? The potential energy, the kinetic energy, the potential and the thermal energy, and now all the rest is just that nozzle flow stuff, essentially. So this is your propellant mass flow rate. So just like you mentioned, if you know this mass ratio here, and you know what the total is, which is 1.5, now you can determine how much fuel and how much mass going out, right? Fuel and ox, sorry. So now that we know this, now we can determine the throat, what the area needs to be at the throat so that Mach number equals 1 at the throat. So now that phenomenon or its inverse works. And so you just use this equation. Your m dot is your total mass flow rate, which is the 1.15. Your P naught, 1,000 psi, right? Your chamber PSA, chamber pressure in SI units. The temperature, which we just have from NASA CEA, right? That's the temperature in the chamber. R is just a property of your M bar, right? So from NASA CEA, gives you an M bar of 20, and if we take the universal gas constant, we divide it by that. So universal gas constant is like 8314 or whatever. Divided by that, that's what we get. So this is just a function of the fluid, which we got from NASA CEA. This is also from NASA CEA, and that's it. So right from there, now we know what the throat needs to be for it to have Mach equal to 1. And then now that we know that, we can determine the diameter, right? So we know the area, and we know what the diameter is, right? So you can use this relation, get your diameter, so that's what it needs to be. And I don't know what the hell that is up there, but the exit Mach number, we just determined what that was, right? It has to do with your area. Well, this is actually an equation to figure out what the Mach of the exit is, which is in that cheat sheet. So we know all this stuff, right? So now we have your area Mach, so that's what the Mach needs to be. And then now it's like, all right, well, we know what the Mach needs to be, and we know that area Mach relation, we know that this tells you the area is only a function of Mach number. So now that we know that Mach number at the exit, now we can figure out what this ratio is. So that's what we just did here, figured out that ratio. And now that we know that ratio, now we can figure out what velocity is at the exit. And so now that's your exhaust velocity. And so now that can kind of tell you the thrust, the P equals PA, which it does, because that's what we used the equation before. So now you can know your thrust if you wanted to, but now we'll step through, which is actually what we do. So then your ISP is your U equivalent over Earth gravity, that's how much ISP we have. And then our thrust, which we just mentioned, is right here. So this ends up being, what is this? Ends up being 0, I think, but yeah. So then that's where the thrust for 1,000 psi is around 750 pounds. So any questions on the nozzle? No? Yeah?
Maybe a dumb question, but why isn't there a shock wave?
Jumping back to this. All right, so yeah, your question is why isn't there a shock at the exit? There is a shock or an expansion fan depending on what your area relation is, right? Because it has to do with the pressure differential. We just said the optimum is where PE equals PA. So we're saying the exit of your nozzle equals out there. So there's no pressure differential, so there won't be a shock.
Okay.
You know, that's why it's the best, because there's no shock, there's no energy loss. It's perfect, right? It just comes out there and now it's just chilling with the ambient.
Yeah.
So that's where P equals PA. And then it comes to a thing where if you're it's underexpanded. Underexpanded means that your PE doesn't equal PA. And so your PA, so if you're underexpanded, your nozzle hasn't been expanded enough to equal outside. So that means it's a high pressure. So if it's a high pressure, now all of a sudden you're gonna have a shock. And so you'll have oblique shocks, and then it'll just abruptly like change. And then if you're overexpanded, it means that you've expanded too much, and it uses an expansion, oh no, it's the other way around. Does anyone remember? I always get confused with this. The overexpanded, underexpanded. One generates a shock at the exit, and one generates an expansion fan.
Expansion
Overexpand.
causes the shock wave, and the under expansion causes expansion wave. I think.
Yeah, I think it might. Yeah, I think it is.
Mach disk, the Mach diamond is caused by shock wave.
Shock waves.
Yeah. That's overexpansion.
Yeah. So like what ends up happening, like if you look up a shock wave, you have overexpanded, meaning that it's expanded too much, that it's still really low, and that
The ambient pressure is higher than the exit pressure, and the ambient pressure will generate a shock wave.
yeah.
under exit pressure.
Yeah, because it wants the pressure to increase.
Yeah.
So across a shock wave, the pressure jumps.
Okay.
And so when you're overexpanded, then that means you have a shock wave because it wants to be what it is outside. And so it generates a shock, the pressure jumps, and then you end up having an expansion fan, right? It ends up being a series of shocks and expansion fans until it ends up equaling outside. And that's why you'll see they keep going because it's slowly going to what it is outside. And then it's the other way, if it's underexpanded, you'll have a huge plume. And that's why you'll see when it launches, when it's going to space, it's getting closer to zero, which means it expands longer. It can't do that, and so all of a sudden, the flow keeps going, right? It keeps making that shape, and that's why it's a huge plume, because it keeps expanding to what it equals outside. So yeah, thanks, Emma. So did I answer your question?
Yeah.
Yeah. Martin?
You might have mentioned it, I forget. Other than mass flow being different, why the two different choices for nozzle between one engine and two different engines?
So exactly. So that has to go. That's kind of in here, but it's more to do with we maximize Hydra's performance, right? Let's see, which equation do we get to show you that? Yeah, area of the throat. So this equation here, right? So.
Oh no, but we double the pressure.
Well, yeah, but not taking that into account yet, right? So say we have one engine, we're at 1,000 psi and a mass flow rate of 1.8 or 1.157, right? And we have two engines, but we were already operating at the most Hydra could push out, right? So that if you have two engine, how much mass flow rate is going into one? Half of it, right? And so if that ends up happening, that ends up having this. So if that's half, then this now is not the same, right? And so that ended up being, this kind of is not completely why we have two engines, but it is why it's half the pressure. So if you notice, when we have two engines, it's half the pressure. And it's half the pressure because we have this, and so if we have this, now this is the same. And so now they could operate at the same throat. The reason why the area at the exit is different is because PE equals PA, right? And so if the chamber pressure is 1,000 and the pressure is slowly going down as you go across, to go from 1,000 to ambient needs a longer nozzle than to go from 500 to ambient. And so then therefore your nozzle's smaller. So that's that. And then, so now we have the thrust, right? We just did the nozzle calcs. Literally that's all you need to figure out how much thrust. Now it's all right. Now we want the chamber to be a certain volume. We know the volume, right? We use this equation, determine what the volume needs to be, based off the L star and the A star, which we just calculated. Now we know the volume, but that doesn't tell us how long it needs to be and how the diameter needs to be, right? So how do we determine that? It's also empirical stuff, which is from a lot of textbooks that you pull for rockets. It ends up being like this curve. This is a characteristic curve for our own chemistry for that, and it has to do with AC over AT. So AC meaning the area of the chamber to the area of the throat. We know what the area of the throat is, right? So we just determined that, and we know the area of the throat, and we know the diameter of the throat, and now we can plug in this equation, right? So now that we know the diameter of the throat, we plug DT in, and now we can figure out what AC over AT is. So we do that, and we get AC over AT is 6.59, right? So that just means the area of the chamber needs to be 6.59 times bigger than the area of the throat, is what they suggest. And then that ends up being, then we know the area of the throat, which we calculated, and now we can figure out what the area of the chamber is, right? So now that we know the area of the chamber, and we calculated the volume of the chamber, so now what did that tell you? We know the area and the volume. So now you know what the length needs to be to get that volume, right? And so now we can calculate how long it needs to be. And so we get 7.51 inches. So you'll notice here, and I mentioned this in the CDR, is that we have a starting point and what we ended with. So this ends up being more of an eyeball test than it is. This isn't gold, right? This isn't like Nozzle Flow where you need Mach equals 1 at the throat or else it won't work. This is well, we want it to be perfect. We want to have optimum combustion. So we've seen in the past, this is the kind of engine that it should, this is the kind of size it needs to be, but it's not like gospel. So then now you end up doing an eyeball test. And this is like one of the emails that, who was it again? It was, who made the pancake spaghetti email back?
Pancakes and pencils, that's in Rocket.
No, not spaghetti, but it was Yuha. Yuha replied to email when we sent like one of the easier one of these that we taught to base 11, the spaghetti and the pancake. He called it. It says pencil in that book.
Yeah.
So this is like the eyeball test. It's kind of like this is what the book told us it needed to be. It's kind of hard to tell on this scale, but it ended up looking very long and skinny, like a piece of spaghetti, right? And so it's just like, this doesn't really look like an engine. And then if you were to do the other way, so this here is the area, right? And so they all have the same area. It's just a matter of the diameter and the length. And so that ended up being what it, And then we ended up here, is where we ended at. So I should have changed that. I forgot to change that.
Should that be they all have the same volume?
Yeah. No, because the area is the length and diameter.
The diameters is changing. The volumes are the diameter.
This last minute. So volume, area, and length. Yeah, you're right. That's a mistake. That should be the same volume, and we changed the area a little bit to give us a certain length. So that's actually I have to make that edit. But yeah, Mike's right. So we have a certain volume, and then depending on the area and length, we could change around. This is the area that they recommended we should operate at. So we kind of changed the area plus or minus to kind of give us a good diameter to length that we think looks good. So kind of ignore those numbers then. This was literally, like I said, did all this today. A lot of this I put together. So essentially, if you change the diameter to length, you have something long and skinny or short and fat. And so essentially you end up with something that's like, all right, this looks legit. And so that's kind of where we ended at. And that's what I mean down here saying this was the starting point, this is what we ended at. So we ended up, it wanted us to have a length of 7.5, we ended up with 6.5. So yeah. And that also kind of had to do with the graphite you could buy off the shelf, that we wanted to buy it so that the diameter ended up being something easy and cheap with minimal machining, so that's cheaper, and the length could be so that we could use one rod for a ton of nozzles. So it kind of like ended up being like a few things in mind, but that's essentially where we got there. And
so
then
it's more like a pencil.
Yeah, I think it's more, yeah, but if you look at other cross sections, so another thing to mention, you'll read it if you look through the books, that this does not translate to small engines and big engines. Like if you ever go look at the F1 engine for the Saturn V, the chamber is literally like this little guy. But then other engines end up looking, so this ends up just looking more like the engines around our size that we're making. So, yeah, I don't think it really looks like it. I mean, this is over-exaggerated because this is what the book said, this is where it ended up, and I just told Mike to just make something that was the other end, so this ends up like looking good. Something
I don't know, I think that's what the F1 engine looks like.
Yeah, maybe, yeah, that's a good point. Yeah, like I said though, it's not bed in stone, it's literally what people have done, so it's not like the most. So now this is for the nozzle length, right? So I kind of just mentioned what the nozzle needed to start and ended at, and what the chamber is. But now we don't know though how long the nozzle is. We know what it needs to be, and we know that it needs to be a slow varying cross section, but how long does that need to be? And that all has to do with efficiency. It all has to do with nozzle flow and having like flow separation or losses and things like that. I think you might have covered it. You might cover it in advance. I'm not sure, but essentially for our nozzle, which is conical, there's two types of nozzles, like conical and bell-shaped. Valerian's bell-shaped. This is conical. Conical is just easier to machine because it's literally a cone, versus the bell-shaped is like a bell. So that's kind of, yeah. So this here actually is bell-shaped.
Did you use that because that's bell-shaped?
Yeah, we use this just to figure out what these radiuses
are.
Okay. That was just there. So for the conical length, this ends up being that around 15 degrees is the best angle to have your inside of your throat. Like your inside of the nozzle, it should be expanding at 15 degrees. And so we know where it starts at and where it ends at. So if we know what the end and the start is and what angle it is, you can figure out how long it needs to be. And so all that is literally just this equation. So we know the diameter at the end because P equals PA. We know the throat because Mach equals 1. And we know this is 15 degrees. So what is the length? And so that's what we use to figure out how long the nozzle needs to be. As you can tell here, it's the diverging part. So it's right where the throat is. And which isn't the end of the world. I think this range that they recommend is like 10 to 20 degrees or something like that. So you just pick the middle. And then these radii here, like I mentioned, is to figure out what shape this converging, diverging needed to be. You just plug in the radius of the throat to those there. Yeah, and then this is, yeah, question?
No, I'm just curious about how do you figure out the throat, how do you call it, the radii?
Oh, this is from a book. I probably should mention. This is literally from a textbook in terms of how they do that. To be honest, I have no idea. It's a picture in the textbook. It says to do it, so I did it.
Yeah.
Mike might know.
No.
No?
Just
Yeah.
did it.
Just listen to the textbook, you know.
All the textbooks are suggesting the same values.
Yeah.
You know, the Russian textbooks are
Good
using the
enough to
same
work with.
values, so I think.
Yeah.
How do
So-
you determine by where do you start the radii? Like,
Oh, that's just
They're all
general
like-
drawing. So that's like if you have an imaginary circle,
yeah.
what the radius would be, like what it would be.
Yeah, I
But
mean,
if you
where
make
the-
them all in like when you do your sketch in NX, if you have all the lines like make them tangent to each other, it like that's the only kind of solution that it sits on.
Yeah.
And you like would define your throat
They
thing
apply everything.
and your exit and your angle, and then it's like one solution.
Okay, yeah, thanks.
Is the reason for that, like to maintain the quasi simulation part where it's like a slowly changing thing?
Yeah,
Or is
it's
that-
just like a smoother transition. You don't want like an abrupt change. Yeah, you want the flow, like all the time, usually you want your flow to slowly go somewhere, right? It ends up being like the most efficient, right? Because if you have a huge step, you're gonna have a huge loss because it's like you're trying to, fit something in all of a sudden a smaller area. The pressure is gonna change quickly, which ends up to losses and things like that. So you might see though, like the converging part doesn't really matter as much as that diverging part, because at the end of the day, like going to Mach 1, it ends up just doing it. So it doesn't really matter. It's just this flow, because if you want the most efficient nozzle flow kinetic energy out of there, so you kind of want that to be the best.
What are the two different radii then? Like 1.5 and 2?
So this is the radii for this, and that's the radii for this.
It's empirical. It's just suggested.
Yeah.
Yeah.
Just to add one more comment on this. So, I mean, I just learned something from another class. So the theta sub 4 and value, the angle, should be decided by what kind of propellant you are using. Like for different propellant, different combustion products, the angle of theta n will be derived from the propellant properties.
But we're not actually using that because we're not using bell shape.
Yeah, but I'm just adding up.
Oh, right.
Yeah. It's roughly in a range from 20 degrees worth.
Yeah. The next page in the book has like every different theta n you can choose, and all like the different lengths and the different efficiencies.
Yeah. It's about efficiency for different propellants.
Yeah. So, and then so these are just a summary of everything we just mentioned. So, all this stuff is what we just covered. So essentially, that's how you do it. So we did that, and then now you just have to worry about cooling it, and this is the sort of stuff that like you do this once, and then you kind of just move on and never do it again, and hopefully you don't forget what it is, write it down somewhere. So. Yeah. So, but this though, like if you were at a company like SpaceX, for instance, this for Raptor, this changes all the time because it ends up being that you pick a design point, but then now you're like, all right, everyone, this is what we're operating at. This is what it needs to be in the chamber. This is the pressure you need to give to me. And then they go in and someone's working on the pump, and it's like, damn, you want that high of a pressure, and you're starting at that low of a pressure. I'm going to have a ton of cavitation, or I'm going to need I'm going to need a multi-stage pump to have that sort of pressure that you want to generate, right? Because, like for instance, Elon wants 300 bar in the chamber, which, like, what's 300 bar? 300. 4,300 psi in the chamber, which is, I think the SSME is the highest one right now with like 3,000 psi roughly. So it's another 1,000 ps. So it's a high pressure, and the tanks are very near atmosphere. So then all of a sudden it's like, well, now we need an extra stage. Well, now it's going to add a lot of mass, so we don't have room now for it. And then all of a sudden, oh crap, let's put it a little lower, and then this changes like 5 times a week. So it's like, all right, and so, but it's a pain in the ass because everyone calculates everything based off of this, but then now it changes, and it's like, well, now I got to do it all over again. And that's kind of the whole process that Mike and I are mentioning, having GUIs and having things to automate these calculations, because the design's changing 100 times, and you want to just quickly, to generate it. So it might take a little bit more time in the front end to generate a code, but in the long term, it's going to save you time. It's kind of the idea. So
that's not even getting to the stage where you actually start processing test data.
Oh yeah. That's all like to generate it the first time. Yeah. So
when people write things like that to make those calculations for you, what language people usually use?
I mean, I don't know at all companies. I mean, I can say it's SpaceX. It's like it's just like shit that I do. I don't like write a MATLAB, or someone will write a Python. It's not like a standard. It depends. I mean, I'm sure NASA has their own wasted a couple years generating a perfect thing, and then, but for startups, it's typically like we need it done now, like just whatever, figure it out, sort of thing. So yeah, but it ended up being like, if you take the turbine design class, like that code that you generate is literally what SpaceX just, because the same professor that teaches it designed all the turbines for SpaceX. So he did the code there, and then now you do the code here. Obviously the code there is a lot more going on, but it's still the same thought process. And so that's something that didn't have for the Merlin engine, but now have for Raptor, which is pretty useful. And like I say, things change every day, so it's so nice to have a code that just every day, like you could change it. So but there's a lot of things. I mean, in terms of figuring out like the optimum exit area, right? You want P equal PA, but if you think about it, like the Falcon 9, for instance, there's 9 engines. But if you wanted the most optimum exit area, it would be bigger actually. And so you would have a larger area. And so if you have 9, now the actual whole vehicle needs to be larger to compensate those 9 little areas. And then now when that's bigger, now the walls need to be bigger. And now all of a sudden it's more mass, and it's like, oh crap, thrust to mass is not worth it. And then it's just all iterations. So, yeah.
So, quick question. I'm just thinking about, is that possible to add all these kind of considerations for turbo pump, for all the things at the very beginning of the design phase, kind of like just roughly figure out what kind of pressure the turbo pump can reach, or at the very beginning, instead of keep changing iterations?
Yeah.
I'm just thinking, is that possible? Or
Yeah. I mean, for those specifically, we could pull up the code that Mike and I did for the class, but that's what the whole design point is like you'll desert. This is more simple of might as well just pull that up. This is a very simple consideration. Like our design point was the pressure, the mass flow rate.
Yeah.
That's it. And so that ends up with a certain temperature. And so technically, if that's your design point, you go into it, and then someone is like, crap, that's too high of a chamber pressure, I can't cool that. And then now it's like, all right, well, how do we get a lower chamber pressure? It has nothing to do with mass flow rate, it has to do with pressure. So then now you might change the pressure, or the OF, or the OF. So it's those sort of things, but
it's kind of like it's too hard to make all the values correct.
Yeah, so you typically start a design. Let me pull.
But like the other thing is they've got to invent stuff to make it work.
You need to get somewhere.
Like they can't do it right now, but they've got to invent stuff.
Oh.
And that's kind of what the idea of this dev engine was. Is that like we're not care about performance. We need just something to test and then to like learn from, and then make the perfect one after. That's why you always hear people making dev engines prior to real engines. Like this is for the presentation for that class is, you'll start at this operating condition, a design point.
Zoom in a bit.
Yeah. So this is like for that class, this is what your project is. He gives you a sheet of paper that says this. This is your design point, make a turbine that does this. And then that's what you need to do. So this is essentially what a designer does, is they'll give you the operating conditions. So it's, all right, we're concerned with making one of the pumps. Which one did we use, the aux or the fuel? I don't remember.
It was the fuel.
The fuel. So this is the fuel turbo pump, the aux turbo pump. Build the turbine for that based off of these conditions. What the inlet pressure is, the inlet temperature is, vapor pressure, density, discharge pressure, right? This is what you need to get. This is what the tanks are. Volumetric flow rate and how fast the shaft is and how much power it needs to produce. So like these are all the things, and then the working fluid, what the properties are for it, mass flow, temperature, blah, blah, blah. Oh no, this is the pump and the turbine. Yeah, sorry. So what the pump is, what the turbine is. You needed to take this and then make it.
Oh, so this one doesn't have any gas generator or like pre-burner, just the expander?
No, it's expander.
Okay.
Yeah. So, so yeah, this is the turbine, and so now we take that, and this is our initial sizing. So this is kind of what you, Hamo, mentioned, like a starting point. And so what the equivalent would be, what I just showed you is your starting point.
Okay.
And then from there you move. And so using similar equations to take into account losses and how turbines work and all that sort of stuff, hand calcs get you to this. And so hand calcs in like MATLAB loops get you to this. And then from this, you now generate turbine. This is the GUI that Mike mainly wrote, which then that's why I wanted to do one for the Jessie James. But like you would input this stuff, which is what is from the hand calcs, into here, and then now that pumps out. From there, we'll give you hand calcs in terms of the geometry of a 2D blade, and then from a 2D blade, you could generate. And these are your triangles, your velocity triangles, and then from there. And then you could figure out what the radius is at the hub, mean, and tip of a blade, and then from there you run CFD. And so now you could take a 2D design, run a 3D CFD, and then you get a result, and then now you compare it, and then you keep iterating on so you get what works. This is like the whole GUI if you wanted to like read through it, but I was working on a thing to make it seem. So this isn't for the course. This is for Jessie James. How many lines is it? 2,500. But let's see. I haven't ran this. So the way this GUI works, like I just mentioned, right? You have the design point here. You press calculate. This now goes on the NASA CEA website, runs the whole NASA, inputs all this for you, runs the simulation, takes the text file, imports it, and then now pulls it from the text file, displays it, and then now those equations that we just all went through, remember, that it was like those take forever to do by hand. You literally just press this, and then bang, it's there. Now we know the OF ratio, M dot, A star, D star, ME, DE, ISP, chamber volume. Right?